All right, what I want to do in this video is talk about a process of proving some sort of statement. And this process is called mathematical induction. Okay, this has nothing to do with induction. If you've heard it in any other context, this is a different thing. So mathematical induction is a way to prove, let's say we have some statement. And so let's say we have some statement P of n, where the first example that we'll do just to make this concrete is, let's say we want to prove that if I take the sum of the first n integers, so 1 plus 2 plus 3, for sum of the first n positive integers, all the way up to n, we end up with this nice formula, n times n plus 1 over 2. So I want to prove that that statement holds for all n greater than or equal to 1. So the P of n part is this part. This is the statement that we're trying to prove. And then we want to prove that this statement's true for all values n greater than or equal to 1. So that's our goal. And so what I want to do is in this video is two things. I want to introduce the idea of mathematical induction, and then I want to show it to you in action with this one example. And so here's the idea. First, there's going to be two steps. So two steps. So first, we're going to prove that P of 1 is true. In other words, prove that the statement is true when n is equal to 1, and that's trivial. If I add up the first one integer, I get 1. That's the left side, not very exciting. On the right side, on the other hand, if I plug in n equals 1, what do we get? We get 1 times 1 plus 1 over 2. And so this is an equation that says 1 is equal to 2 over 2, which is true. It's important that we have to check that this first step's hold, even though it's typically this trivial. It's pretty straightforward. So that's the idea for step 1. This is called the base case. Step 1 is called the base case. And then step 2 is we want to prove the following. We want to prove that if P of k is true for some k, then P of k plus 1 is true. Now, we want to prove that if the statement is true for some value k, then it must also be true for the next value, k plus 1. So what this does is the following. The second step, by the way, is called the inductive step. So this is called the inductive step. Okay, so there's, again, two steps here. And the way that this is going to work is as follows. So I want to prove that some statement is true for 1, 2, 3, 4, 5, 6, 7. You can go as far as you want. We checked that the statement's true for 1. So we don't have to do any more work. We know that it holds for the first step. We know that the formula is true when n is equal to 1. And once we've proven number 2, once we've proven this inductive step, then we get all the other integers from those two steps. And the way that we do that is that we already know that 1 is true. And then we showed that if 1 is true, then 2 is true. So that implies that it's true for 2. And because we're using the fact that if it's true for 1, then it's true for 2. And then we know that if it's true for 2, it's true for 3. And if it's true for 3, it's true for 4, which means it's true when n is 5, which implies that this is true when n is 6, which implies that this is true when n is 7, and so on. And so this actually shows, once you have both of these steps, this actually shows that the statement must be true for all positive integers greater than or equal to 1. I think of this as a big game of dominoes. You push over the first domino, and then the second step, this inductive step, ensures that whenever you push over the first domino, that sends the rest of them going. So this is a big game of dominoes. Or another analogy that gets used frequently is a ladder, right? You can get on the ladder, that's the first step, and then as long as you can get to the next rung, that's the inductive step. So whatever metaphor, whatever idea you want to use here is fine. let's actually employ this and prove the statement for the sum of the first n integers. So let's just start over, and let's actually prove that 1 plus 2 all the way out to n has this nice formula, n times n plus 1 over 2. Let's prove that this is true for all n greater than or equal to 1. Greater than, come on, pen. For all n greater than or equal to 1. Now, the base case is going to be our first case here, which in our case is n is 1, and we already checked that that's true, but just so that we have this all written in a nice, succinct way, let's do it again. So our base case corresponds to n equals 1, and that says that 1 is equal to 1 times 1 plus 1 over 2 is true. The base case is usually not a long process, but it turns out to be an important process. It's crucial. For the inductive step, what we're going to do for the inductive step is as follows. We're going to say, suppose that, we need to be a little careful here, but assume that P of k is true for some k. In our case, it's for some k greater than or equal to 1. We used 1 because that was the base case. So assume that P of k is true for some value k greater than or equal to 1. We want to show our goal, we want to show that P of k plus 1 is also true. Okay? I want to be very careful and very nitpicky here. This is important. I'm not assuming that P of k is true for all k, because that would be circular reasoning. We're trying to prove that this statement holds for all n. So I'm not allowed to just assume it holds for all k or for all n, because that's circular reasoning. We're not doing anything. We're saying if it's true for some k, then it's got to be true for k plus 1. Okay, that's a distinct idea. That's different. And I shouldn't, I want to go back actually. I don't want to write P of k. I want to actually write the statement where we're using k's instead of n's. So P of k is going to be the statement where we're using k's instead of n's. Let's do a little iPad rearranging here. So I want to assume that P of k, so I want to assume that 1 plus 2 all the way out to k has a nice formula that this is k times k plus 1 over 2. And I want to assume that that's true for some k. And then given that, we want to show, so sorry again to rearrange here, but we want to show that P of k plus 1 is also true. So what that means in our case is we want to show that, what does the statement say when n is equal to k plus 1? Well, we want to show that 1 plus 2 all the way out to k plus 1 is equal to k plus 1 times k plus 2 over 2. So this is our last value, and then n times n plus 1 over 2, where n is k plus 1. So that's the formula. So that's what we're after. And we're assuming that this statement is true for some k greater than or equal to 1. So what this means is, let's look at this last sum, 1 plus 2 plus k all the way up to k plus 1. And I want you to notice that in that sum is actually the sum of the first k integers, which is something that we're assuming has a nice formula. So by our assumption, okay, by our assumption that 1 plus 2 plus k has this nice formula, so by our assumption, we know that 1 plus 2 plus all the way up to k has a nice formula, k times k plus 1 over 2. And therefore, if I look at the sum that we're considering, 1 plus 2 all the way out to k plus 1, what we can do is we can kind of group off the sum of the first k terms, and the first k terms add up to k times k plus 1 over 2. And then that's supposed to be equal to k. So we know that this sum from 1 to k has a formula by assumption, and then our last term we're just keeping there. Okay, so I'm replacing the thing in parentheses with k times k plus 1 over 2. The following step is just algebra. So we're going to multiply and divide by 2 to this k plus 1 term to get. So we're going to put a 2 up top, put it in the denominator, and then now we can add up the two fractions. In fact, there's a 2 in the denominator, so that's fine. There's a k plus 1 in the numerator that we can factor out, and we're left with k plus 2, which is exactly what we wanted. So I'm going to put our little box there that indicates we're done with the proof. Okay, so that's how that's going to work. That's our first example of mathematical induction. One last comment, actually 2 more comments. One is that the statement that we assume is true. So the statement we assume is true for some k, in our case greater than or equal to 1, is called the inductive hypothesis. So that's a word that'll be useful for us. So this is called the inductive hypothesis. This is the statement that we're assuming is true for all k, for some k greater than or equal to whatever our starting point was. Okay, so that's called the inductive hypothesis. And then my second comment is that I want to talk a little bit about the strengths and the deficiencies of induction. The strength is that it's a nice way to prove a statement. But the deficiency is that maybe the inductive step is hard. Maybe this is not a great method. It's not going to be the end-all be-all of proving a statement necessarily. But more to the point, induction never tells you what to prove. You had to come up with this formula on your own, and then you can check it with induction. So induction is not a method that we're going to use to predict a formula. It's going to be a method that we'll use to prove that a formula is true. Okay, so just I think it's good to keep that in the back of our mind just for reasonable expectations. Okay, but there's our first example of mathematical induction. So in the coming videos, we'll talk about a few more examples.